Welcome to homework.
Okay, so the equation for the alpha emission in this case should be U238 to 4 helium plus 234 thorium. Since we know that the alpha particle is helium-4. So the change of mass, which is delta M here, can be equal to mu minus mhe plus mth. So we know the mass for the uranium is 238.0507 AAU. And the atomic mass for the helium is 4.002603 U. The atomic mass for the thorium is given as 234.043601 U. If we do some calculation here, we have the change mass is equal to 0.004584 U. So now we can determine the total energy that was released, which is equal to delta M times C squared. So we know C squared can be expressed as 931.5 mega electron volt per U. And we know C squared here is the square of the speed of light. So now let's plug it back to the equation to determine the energy that was released, which is equal to 0.004584 U multiplied by 931.5 mega electron volts per U. And this will give us the total energy that was released should be equal to 4.270 mega electron volts. So now let's take a look at the next question. So we know kinetic energy can be equal to 1/2 mv squared, which is also equal to p squared over 2m. In this case, we know the momentum is conserved, since the momentum for the alpha particle is equal to the momentum of the thorium. So therefore, we can set out such a ratio here, which is k alpha over kth. If we expand it, we have p alpha squared over 2m alpha over pth squared over 2mth. Since we know the momentum is conserved, that means p alpha should be equal to pth. So as you can tell, p alpha squared and pth squared can be cancelled out, and 2 here can be cancelled out as well. So eventually we have k alpha over kth is equal to mth over m alpha. So if now we just do some arrangement here, we have the kinetic energy on the thorium should be equal to m alpha over mth times k alpha. And we know the kinetic energy for the thorium can be equal to 1/2 mth times v rec to the power 2. V rec here is the recoil velocity for the thorium nucleus. So now if we do some arrangement here, we have the recoil velocity is equal to square root 2 m alpha k alpha over mth. So the kinetic energy for the alpha particle should be equal to the total energy that was released according to energy conservation law, which is equal to 4.27 mega electron volt. If we convert it to joule, it's about 6.832 times 10 to the power of negative 13 joule. And we know the mass for the thorium is 234.043601 U. If we convert it to kilograms, it's equal to 3.885 times 10 to the power negative 25 kilograms. And the mass for the helium in kilograms is equal to 6.644 times 10 to the power of negative 27 kilograms. So now we can plug in back to the equation to determine the recoil speed, which is equal to square root 2 times 6.644 times 10 to the power of negative 27 kilograms. And then multiplied by the energy, which is 6.832 times 10 to the power of negative 13 joule over 3.885 times 10 to the power of negative 25 kilograms. And this will give us the recoil velocity for the thorium nucleus should be equal to 2.453 times 10 to the power of 5 meter per second. And these are the answers for this question.